Imagine a popular online store during a big sale. Thousands of users are browsing products, adding items to carts, and checking out simultaneously. Behind the scenes, millions of pieces of data are moving through the system. Customer information, inventory updates, payment transactions. Suddenly, the database starts slowing down. Queries take longer, pages lag, and some users can't complete purchases. The system isn't broken, it's just overwhelmed. Modern applications need to handle this scale without crashing or slowing to a crawl. One of the key ways engineers manage is called partitioning. Partitioning helps distribute data and work across multiple storage units or streams so that systems remain fast, reliable, and organized, even under heavy load. Today, we'll explore what partitioning really means in data systems, how it works in databases and Kafka, a distributed event streaming platform, and why it's essential for building systems that scale gracefully. Think about apps you use daily: social media feeds, streaming services, online banking, or e-commerce platforms. All of these systems deal with massive amounts of data. Without careful organization, a single database or a single stream can become a bottleneck. For example, imagine a music streaming app that stores every user's playlist and playback history in one big database table. If millions of people are accessing it at the same time, queries slow down. Searching for songs, loading recommendations, or updating playlists becomes noticeably slower. Users get frustrated, even if the system is technically working. A similar challenge appears with message systems like Kafka. Companies often rely on Kafka to process real-time events, like orders, clicks, or logs. Without partitioning, all messages might flow through a single queue. One slow consumer can hold up others. The system appears jammed, and delays ripple outward. The problem is not with the idea of databases or event streaming itself. The problem is scale. Systems need a way to spread the load, manage concurrency, and maintain order without slowing everything down. Partitioning provides this solution by splitting data or streams into multiple, manageable segments that can be processed independently. A helpful analogy for partitioning is a warehouse with many aisles and bins. Imagine one huge warehouse with all products stacked together, without any order. If a worker wants to retrieve a specific item, they have to search through everything. If multiple workers are looking for different items at the same time, they get in each other's way. Now imagine the warehouse is reorganized. Each aisle handles a specific category, each bin a specific subset, and workers are assigned to sections. Everyone can work in parallel without interfering with each other. Database partitioning works in a similar way. A large table is split into smaller, distinct pieces called partitions. Each partition contains a subset of the data, perhaps by date, customer region, or product type. Queries and updates can now target only the relevant partition, making operations faster. Kafka partitions work like multiple conveyor belts in a warehouse. Each belt handles a portion of the messages, and consumers can process them in parallel. Yet within each belt, messages remain in order, so workflows remain predictable. Partitioning does not remove the work. It organizes it so multiple processes can operate efficiently without conflicts. In both cases, the system is easier to manage, more resilient, and ready to scale. Let's look at a concrete example with a database. Imagine a global e-commerce platform that stores every customer's orders. If all orders were in a single table, queries like, "Fetch all orders from Europe today," would require scanning through millions of records. Instead, engineers use horizontal partitioning, also called sharding. Orders are divided into separate partitions based on geography. As one example, Queries targeting Europe only hit the European shard, not the entire dataset. Performance improves dramatically, and other regions continue operating normally. Now consider for instance Kafka. A large ride-sharing company might use Kafka to handle trip requests. For example, each city is assigned a separate partition within the topic. All messages for New York go into one partition, all for San Francisco in another. Consumers in each city can process trips independently and in parallel. If New York experiences a surge, San Francisco processing is unaffected. Partitioning enables parallelism, maintains message order per functional key, and prevents a bottleneck in one area from slowing the entire system. These strategies are invisible to the user but critical for ensuring systems remain fast, reliable, and scalable, even during peak demand. Partitioning matters because it allows modern software systems to scale gracefully. Systems today handle vast amounts of data and requests every second. Without partitioning, a single table, queue, or stream can quickly become a choke point, slowing everything down. With partitioning, systems divide and conquer. Each partition can be processed independently, updates are localized, and queries are faster. For engineers, this reduces risk. Updates or failures in one partition do not affect the rest of the system. Maintenance becomes safer. Testing changes in a single shard or partition is less risky than working on a monolithic dataset. For users, the impact is subtle but profound. Apps remain responsive, messages are processed quickly, and data is delivered reliably. Partitioning also allows organizations to grow. As traffic and data increase, additional partitions can be created to handle the load without redesigning the entire system. In short, partitioning is a foundational principle that balances performance, reliability, and order, making large-scale systems possible and manageable. When you step back, partitioning is more than a technical trick. It reflects a way of thinking about complexity. Divide, organize, and process efficiently while preserving order. From databases storing millions of orders to Kafka streams delivering millions of messages, partitioning allows systems to scale without breaking. It quietly ensures that operations continue smoothly, even when demand surges or unexpected events occur. Users rarely notice it, but every fast query, every timely notification, every seamless transaction depends on this principle. Partitioning reminds us that in both technology and life, thoughtful organization can prevent small issues from becoming larger problems. It's a quiet, invisible design choice that keeps modern systems running reliably, allowing engineers to build with confidence and users to interact with trust.